And you've got card key access. You also should get card key access to BWRC, but I think that has to do. So this would be Core A117, and I think BWRC you have to do it separately, but for now.
If they don't let me, I'll come back.
Okay.
About Friday,
Mm-hmm.
this year we have a meeting.
Mm-hmm.
Um,
Can you make it 4 to 5? Okay.
4 to 5. Where is it?
It'll be at BWRC, in fact. I'll make an announcement.
Okay.
Yeah. Just send me an email so I can put you on my list so I remember.
All right.
All right. Thanks. There's some room inside here, guys. There's a seat inside here. Okay, let's get started. Welcome to EECS 142, Communication Integrated Circuits. My name is Professor Niknejad. It's the second time I'll be teaching this course, and taught it last year. It was a lot of fun. This is the first time I'm actually teaching it in this classroom, so the dynamics will be a little bit different because it's going to, I'm used to writing on a blackboard. Let me also introduce Al Molnar. He's going to be your GSI this semester. Let me just say you guys are very lucky to have Al as a GSI. He's a very experienced RF designer. He spent several years in industry. He was part of a team that built one of the first fully integrated transceivers for cell phones. So you guys are really lucky you have a great GSI this semester. Okay, let's get some of the administrative things out of the way. First of all, let's switch over to the computer here. This is our class website. Email address or the web address is basically RFIC EECS Berkeley EDU Niknejad EE142. If you go to my website, there's a link to it. If you also go to the instructional website, you can get to it. Everything you need for this class will actually be on the website. So I won't be, making any photocopies or handouts. All the homeworks will be posted on the website. So basically, make sure you check the websites regularly. In particular, the lectures. If you click on the lectures link, I'll post the lecture notes at least a couple days before the actual lecture, so you can print it out and make notes on it if you like. Otherwise, you can just follow on the screen during lecture. Let's see. So this course, we'll talk a lot about what we're going to learn this semester, so I won't go into that now. some of the other logistics. Um, these are my office hours. These may change. Uh, in particular, I probably will not be able to hold tomorrow's office hour Wednesday, but definitely Thursday I will hold it. But it'll be Wednesday, Thursday from 10 to 11 in my office, which is in 572 Corey. There's two discussion sections which will be run by your GSI, Al Molnar. And in particular, he would like to make a change to the second discussion section. So we have a discussion section on Monday 2 to 3, which stays, right? And then Tuesday, there's a discussion section from 5 to 6, which he'd like to change because it conflicts with the seminar. So you guys who are enrolled in that discussion section should discuss. I guess Al will take a poll and figure out when's the best time. Um, let's see. So Al's office hours are also here, Monday 3 to 4 and Tuesday 2 to 3. Those are good. Good to go. Okay. And let's see, what else can I tell you guys? Homework. Homework, midterm, final, all that stuff. I've already scheduled a midterm. There'll be one midterm in this course. I'm going to be out of town, so it was a convenient time. It's roughly halfway through the course. Homework is very important in this class, and it's a big part of the learning experience. If you just come to lectures and watch the lectures, I think you'll learn maybe 15%, 20%. It's really going home and doing the homework that'll teach you. Some of the homeworks are a lot harder than others. Some of them require lots of time, 10 plus hours. So be prepared. This class is not going to be a breeze. It's going to be a lot of work. But I think you'll learn a lot, and I think you'll enjoy it. You'll notice that I have two grading scales for graduate students and for undergraduates. By just a show of hands, how many people here are graduate students? It's funny, all the graduate students are sitting on this side mostly. Graduate students on this side are actually kind of weird. No, just kidding. Maybe you guys should mix a little bit more. But yeah, so as you can see, there are a lot of graduate students in this class, roughly half the class. And that's good. That means that for the undergrads in this class, you have some competition. This is your chance to show yourself. It also means that you should make friends with graduate students and learn from them. Peer-to-peer learning is also a very important process. Speaking about peer-to-peer learning, there's of course limits to that, and just to remind you of that, I put a link to the academic honesty policy, which is not working now. It's not online. There is no academic dishonesty. No, there is. It's the Standard Department academic honesty policy, so I encourage you guys to review that. If you have questions about what's allowed and what's not allowed, then feel free to ask me or Al, but I think your common sense should tell you what's right and what's wrong. Certainly you guys can get together and share your ideas on homework and projects and discuss things, but of course you should also do your own individual work, and that's taken very seriously in this course. So if I do find out that there is any kind of cheating, you will be penalized heavily for that. Okay, so that software. Almost every homework assignment that you do in this class requires you to run SPICE. And that's not news to any of you. You guys have been doing that for all the other IC courses you've been taking. So most of you are familiar with HSpice. I encourage you to get your SPICE account up and running and make sure everything's working well. Al is also going to set up an account for himself just so he goes through the process to make sure there aren't any bugs. For the first half of the course, you could probably just use HSpice, which is something most people are familiar with. Second half of the course, you're going to need to run SpectraRF, Cadence's SpectraRF tool, which is able to analyze mixer noise. SPICE can't do that, and we'll learn why later in this course. So at some point, you might want to make the transition a little bit early to Cadence. Cadence also has a graphical environment where you can draw schematics and do all those neat things. But if you like the text interface, that's fine. Whatever is easy for you guys. So try to get the software-related issues resolved early in the course. Now back to the grading policy and the difference between grad and undergrad. You'll notice that for graduate students, homework counts less towards your final grade because you have a project, which counts for 15% of your grade. And the project is a very important part of the course for the graduate students. In particular, graduate students who are just getting started with research. Imagine a lot of the students here today are first-year graduate students. the project is an opportunity to explore some research ideas. So I encourage you to come and talk to me about project ideas. We haven't really set the project yet. Last year when I taught the course, the project was the same for everybody. So it was kind of a design problem. I gave specifications that you had to meet, and it was really good. One of the students, a lot of good projects came out of that. In particular, one student had a really neat idea for a new LNA topology, and he ended up turning that into his research project. So it's a good way to get your research started. Now, how about undergrads who want to do a project? It's funny, last year a lot of people wanted to do a project, even the undergrads, but at the end no undergrads submitted a project. Uh, I hope you guys are better. There is a caveat. If you do a project as an undergrad, you will go into the grad scale. So basically, if you think you're good enough to compete with the graduate students, you can do it and you can do a project. Of course, you can do a project just for learning's sake, and and it will not count towards your grade if you don't want it to. So that's something we can discuss as well. Okay, any questions about these kinds of general issues? Am I missing anything? Okay, so we can get started with today's lecture. All right, and basically we're just going to dive in and give you an overview of communication systems. And a lot of this material will be new to some of you. Some of it will be a review if you've taken other communication courses. But I encourage you to come back to this first lecture later on, because a lot of the concepts we talk about today may not make a lot of sense until you've actually gone into more depth. So this is kind of a generic communication system. Generally, we want to communicate information through a channel. Now that channel can be free space. I might be sending information from one point in the room to another. It could be over thousands of kilometers through cable or through fiber optic medium. It could be underwater through the ocean. So we have all these different channels. There's also some channels that you might not really think about as channels. So for instance, just sending information from, let's say, your laptop, let's say, to a hard drive using a USB cable. Now we don't really think of that as a channel because it's just a wire, but in fact, if you really want to get the most throughput through that link, you do have to analyze it as a communication system. In fact, just putting traces on a PC board can be analyzed as a channel. In fact, if you really want to send lots of data, let's say a server communicating with memory, high-speed memory on a PCB, you have to analyze the communication properties of that channel. Now, naturally, we have a transmitter and a receiver. A transmitter, let's actually back up and start out with the source of information. Okay, so, what do we want to send? It's very obvious. It could be music, it could be voice, it could be just bits, right? And bits can represent anything. But we also will generally take those bits and do something with them. We may compress the bits. We don't want to send more information than we have to. It could be lossy compression or lossless compression. And we generally put coding on the bits. The reason we put coding on the bits is we want to be able to detect errors in transmission, which can be very common for certain types of communication. As you can imagine, if you send information down a wire, it's probably going to be a lot better than sending information through the air, because through the air, the environment is constantly changing. There's multiple paths from source to receiver, so the probability of error is higher. So coding allows us to detect when errors occur and allows us to sometimes even correct for those errors. Now this course is not at all concerned with the source of information. We're concerned with basically taking that information and putting it on top of, let's say, some kind of modulating some kind of carrier and sending that information over a channel. So here we have the term modulator, and we'll talk about why we need to modulate the information in a few slides. And then finally, we need to drive that information onto the channel with a transmitter. And this will involve basically power amplification, because a lot of the channels that we're concerned with are very lossy. Sending information from here to, let's say, a base station, which is a few kilometers away, is a very lossy process. So we need to send as much power as we can. Now on the receive side, it's exactly the opposite. We need to receive the signal. When we transmit the signal, it's large. When we receive it, it's very small. So we need to build a very sensitive receiver. And then we need to demodulate it and then basically turn it back into useful information. Now, the information sink may be a video display, right? It could be your cell phone. It could be a speaker. It might be a couch potato watching TV. It could be a web browser, and so on and so forth. Okay? So any information about the slide? Okay, so for those of you who took 105 with me a while back, you may remember this figure. It's a generic cell phone, and what I tried to do is point out what courses relate to what parts of the cell phone. Of course, you know, we're not here to just learn how to design cell phones. You learn a lot more than that. But this gives you an idea of what courses offer what. So starting out with EECS 117. 117 is the electromagnetics course that we offer here. You learn about waves, wave propagation, you know, transmission lines, and so on and so forth. It's a great course. I highly recommend it. You also learn a little bit about antennas, or how you turn voltages on wires into waves that travel through the medium. 142, you can see here in this dotted box, is concerned with these blocks and these communication building blocks. Now, what distinguishes, let's say, 142 from 140? 140, you learn a lot about designing amplifiers, in particular linear amplifiers. A lot of the blocks that we deal with in 142 are actually nonlinear or time-varying systems. So, for instance, an oscillator is something that has a DC input and has a sinusoidal output. That's a very nonlinear circuit. 140 doesn't really tell us how to design a circuit like that. Another example is a mixer. A mixer performs frequency translation, which is something that a linear system, linear time invariant system, simply cannot do. So that's one distinction between 140. The other distinction is we're going to be concerned a lot, even when we do design quote-unquote linear amplifiers in this course, we're going to be really concerned with the non-ideality of these components. So the noise that's generated by these components and the non-linearity generated by these components. Okay, if you're concerned with the devices themselves, you know, this course is not a device course, it's a circuits course. So we basically will treat the device as a black box with some equations that describe its behavior. But of course, if you're interested more in understanding where that behavior comes from, 105, 130, which is the device physics course, and 143, where you actually learn to build these devices, this processing course. Now, as I mentioned already, this course is the front end. We don't deal with this part, the antenna. We also don't really deal with the digital side of things. So our concern in this class is to take the information in analog form and to basically down convert it to a lower frequency where we can digitize it and then process it with digital circuits. So generally, a digital signal processor is something like a microprocessor that's customized to deal with signal processing tasks, communication tasks. EECS 123 is a good course. 141 is, of course, is the general digital course. If you're doing a custom digital design, then 141 would be where you would learn how to do that kind of stuff. And of course, above the DSP, there's usually a microprocessor and software, and you know, I don't need to tell you guys which courses to take to learn about that stuff. Now, you'll note that 120 is a prerequisite for this course. Signals and systems. The other prerequisite, I believe, is 140. If you haven't taken 140, I can tell you now you're going to have difficulty in this course because we're just right off the bat going to assume that you know how to design amplifiers, how feedback works, and so on and so forth. So if you are planning on taking this course before 140, I would say it's a bad idea. If you're 120 though is not as bad. If you learned 20 really well, you know your signals and systems, Laplace transforms, Fourier transforms, you'll have no problems in this course. So if you're co-enrolled in 120, you're probably in good shape. A couple of other related courses. 121 is a digital communication course. It is the theoretical background of how you build a communication system. Again, we're not going to talk about that in this class. Another course that may help you understand some of the concepts is 126. 126 is random processes and random variables. It basically allows you to understand how noisy signals, the statistics of noisy signals. And you know, by definition, all communication occurs with random signals, right? If you're sending a non-random signal, that's trivial. There's no need to communicate it. So anything interesting by definition is random. So we're building circuits that operate on random signals. And that requires a set of tools In this class, it's very simple, and we'll review those tools when we do deal with noise. Okay, I think I already said all this, so let's skip this slide. All right, so let's zoom in on a receiver and look at the various building blocks that you have in a receiver. I've shown here a pretty generic architecture. It's called a superheterodyne architecture. We'll talk more about why we call it that. One reason is that this receiver, basically using this mixer, first thing it does is it down-converts the spectrum down to a fixed IF frequency. IF stands for intermediate frequency. And we basically do some signal processing at the IF frequency, and we then digitize the signal. So the ADC here is analog to digital converter. These blocks here are filters, and you can see that filtering is a big part of what a receiver does. The first block, though, before we can actually mix the signal, is a low noise amplifier. And the job of a low noise amplifier is obviously to amplify the signal, but to do it in such a manner as to add as little noise to the signal as possible. This is important because, as we discussed, in a receiver the signals can be very small. We also need an oscillator, a reference frequency that lets us do the frequency translation. Again, I know this is all really fast. It's just an overview. We'll go into a lot more detail on this. And so these are the kind of blocks that we're going to be talking about in this course. Amplifiers like this LNA, mixers, oscillators, frequency dividers, VGAs, which are variable gain amplifiers, more mixers, more filters, and so on and so forth. Okay. Any questions or comments? We'll do that in a few slides, but thanks. Yeah. Okay, so what's so difficult about building, let's say, a receiver? It seems like you just need an amplifier, right? And you learn that in 140. Just amplify the signal until it's big enough, and then digitize it. Right? What's wrong with that approach? Anybody? Okay, why don't you use the microphone? Since this is being webcast, they won't be able to hear you.
I'm saying that there's a lot of noise and junk that comes with the signal, too. So if you just use an amplifier right away, you're just going to be amplifying the other stuff too. It's not.
That's right. That's precisely right. So as I've shown in this picture here, you can see that in general you have a channel. The channel is a frequency span over which you're communicating, and this little spike here is your signal. I'm not sure if it shows up very clearly there. And you might have a huge interferer sitting right next to you. Now you might say, well, where did this interference come from? Just suppress that interference. Actually, that interference is someone else communicating over a channel right next to your channel. Or it could be some other source of interference that you have no control over. So you can't simply gain up the signal, your own signal, because then you'd also gain up the interferer, and eventually the interferer would make your system clip. The other issue with just using an amplifier is noise. In many situations, the signal is not much bigger than the noise. And so if we just go into 140 and just basically design an amplifier, you'll find out that it might actually be a noise amplifier. It might actually make the noise bigger than the signal that you're trying to amplify. So pretty soon, the signal that you're trying to detect is lost in the noise. And this noise is something that's ever present. We can't get rid of it. It's a part of nature. It's a very natural phenomenon. Okay. The other issue that Al brought up was the dynamic range of the signals that we're receiving. You don't stand still and communicate, although there are point-to-point communication systems. Even in those situations, the signal strength varies. You might have to design a receiver that has to work over a few meters range to a few kilometers range. And that might mean a huge dynamic range in the signal that you're receiving. And I put a number here, about 80 dB, let's say, for a cellular communication system. This signal varies not just because you move back and forth closer and further away from your transmitter/receiver, but also because the environment over which you communicate changes. In a wireless system, for instance, we have multipath propagation. Now, multipath propagation means that if I'm communicating with, let's say, the base station, which is, let's say, at the end of the room, there's many paths between me and the base station. There's a direct line of sight path, there's a path that would reflect off of the roof, there's a path that would reflect off the ground, there's a path that reflects off that window there, and so on and so forth. And so I'm not receiving just one signal, I'm receiving an ensemble of signals. And depending on the phase of these different paths, these different signals may add in phase or they may actually subtract. And so if I just move basically a few, depending on the frequency of operation, let's say I'm communicating at 10 gigahertz. So 10 gigahertz, the wavelength's on the order of a centimeter. So if I just move a centimeter back and forth, I'm changing the phase of these different paths by an order of a wavelength, so that the phase can change and I can get significant amount of change in the amount of signal I'm receiving. This is called multipath propagation. There's also shadowing, the fact that I could be behind a tree or behind a car when I'm communicating and all of a sudden my signal strength drops a lot, or I might be around a corner, and so on and so forth. And this is all happening in a time-varying fashion, so my receiver needs to detect the signal strength and adapt to it. Okay, so this next slide illustrates what we were saying before. The idea is when you build a receiver, you don't want to throw the baby out with the bathwater. And it's a very appropriate expression for communication. The idea is that this is you're receiving a signal. Let's say you're talking to your best friend on your cell phone, and just by chance you're really far away from the base station. And this is the base station. So the signal that you're receiving is really weak. Unfortunately, you're in a cafe and right across from you someone's also talking on their cell phone. And not only are they talking loud and not only are they annoying, but unfortunately their power amplifier is quite annoying too, because it's transmitting a lot of power, and the frequency could be very close to the frequency that you're receiving. So this is called a near-far situation. You're near an interferer and you're far away from the desired signal. And so this means that your receiver has to be able to deal equally well with small signals, which are very close to the noise, and large signals, which in fact excite nonlinearities in your receiver. So that's the key word, nonlinearities in your receiver. And this is something that we'll talk quite a bit about in this course. So summarizing what we've said up to here, the goal of a communication system is to, one of the first goals of a communication system is to amplify. And again, getting back to what your Al Molnar pointed out was the kind of power levels that we deal with when we design receivers. Now, right off the bat, we use a dBm scale. So dBm scale is nothing but a dB scaled normalized to 1 milliwatt. So for instance, 0 dBm is 1 milliwatt, 10 dBm is 10 milliwatts, and so on and so forth. Now, it's good to know that because almost all the communication equipment that you carry around with you, perhaps even today, has a little signal strength indicator, which is an estimate of how strong the signal is that's coming in. And if you look at your wireless LAN, you might find that a typical signal strength might be minus, let's say, 70 dBm. So if we take minus 70 dBm and just translate that into watts, well, that's 10 to the minus 10 watts, or 100 picowatts. It's not much power, is it? And we can translate that into an effective voltage that you see at the input of the LNA, assuming that your input impedance of the LNA is matched to your antenna with an impedance of Z0. If you just translate that into a voltage, basically we know that the power is proportional voltage squared. That corresponds to 100 microvolts, approximately. Now, that's a small signal, but it's not too bad. We can probably live with that. That's not too bad. 0.1 millivolts. But what about for a cellular phone? Now that at the same time as you're receiving that wireless LAN data, you're also receiving, let's say, a wireless LAN, a cellular telephone call, and the signal there is minus 100 dBm, and the cell phone has to work. Well, how small is that? That's 10 to the minus 13 watts. Using the same formula, if we translate that into a voltage, that's just 3 microvolts. Now that's a really small voltage. And to gain some intuition about how small that is, go in the lab and look on an oscilloscope. Start out with, let's say, 100 millivolts, and then keep making the voltage smaller and smaller. And as you get into the microvolt range, you'll see that it's all blurred out, it's all noisy. That's because of the finite dynamic range of that oscilloscope. And it's also because of the noise that's present with that signal. That noise, as we'll learn about in this class, is proportional to the bandwidth of your observation. And The more data you push through a link, the more bandwidth you need, and therefore the more noise that will enter your system. Okay. Now the other point about communication is that while you're receiving, in that near-far situation that we described, while you're receiving this tiny signal, let's say you're also receiving another signal, which is an interference that's minus 40 dBm. Now again, that's only about 3 millivolts. That's a pretty small signal, right? Nothing to worry about, especially when we look at distortion and large signal behavior of transistors. Yeah, 3 millivolts is a pretty reasonably small signal. But the problem is it's so much bigger, right? It's 60 dB bigger than the signal that we're trying to observe, right? And that means that if we just simply were to apply gain to our system, that interfere would actually limit the gain of the system to about 1,000. In order to take 3 microvolts, let's say up to 300 millivolts, in order to, let's say, digitize it, we need a gain of 10 to the 5. So if we can't get rid of this interference somehow, we can only have a gain of 1,000, which means we're going to have to either give up on communicating when we have interferers, or it means we need an extremely sensitive analog to digital converter, which is going to cost us a lot of money and a lot of power. Therefore, it's not going to be portable. So, of course, the goal of a communication system is to get rid of that interfere, and we'll see how you do that throughout this course. Okay. Any questions or comments at this point? Kevin?
How do we know the difference between the interference signal and the signal we want?
That's a good question. Sometimes we can't tell the difference. In fact, in this class, we'll talk about a lot of mechanisms which produce energy inside the bandwidth of interest, and so there's no way for us to distinguish friend from foe. Of course, if we put coding on the signal, for instance, like a CDMA kind of coding, that could gain up our own signal relative to the interferer. But in many situations where you don't have that kind of coding, you basically have to live with it. And so that's why when we specify the performance of a receiver, we have to make sure that under worst case conditions, the signal is distinguishable from not only noise, but also interference. Now, how do you distinguish basically other like legitimate users of the spectrum? Let's say someone else using cellular band or wireless LAN band. Well, that's some kind of scheduling, right? You either divide the frequency up, frequency division, multiple access, or you have time slots where each person is allowed to transmit data, or as I discussed, CDMA, some combination, code division, multiple access. Okay, good question. Any other questions? Okay, so amplification is a goal, but we just can't do blind amplification. We have to do it very carefully. We have to make sure we do it so that we don't generate too much noise and we don't generate too much distortion, and that we're robust against interferes. Okay, the next goal of a communication system is frequency translation. And as I already mentioned, a linear time invariant system cannot perform frequency translation. So what is frequency translation? That means that you have an input at one frequency and an output that's at a different frequency. And one way to build basically a device that frequency translates is to use a nonlinearity. And we'll be looking at that in this course. Another way to do it is to use a time-varying circuit. And both approaches are actually valid ways of building mixers. Mixers are circuits that perform this frequency translation. We draw them as a circle with an X to basically emphasize the fact that they're kind of taking a product. Not strictly valid, but it's a good first-order approximation. If I take the product of two, let's say, cosines, the output is a cosine at the sum frequency and a cosine at the difference frequency. So certainly products are a way to build mixers. Some terminology, usually for a down conversion system, down conversion meaning we're going down in frequency, like in a receiver, we have an input RF frequency, and generally we have an IF frequency or intermediate frequency which is lower. And in order to generate that lower frequency, we use what's called the local oscillator, or the LO frequency. Now, why do we need to perform frequency translation? Well, that's because we can't, a lot of times, most of the time, we can't just transmit the raw baseband data. The baseband data is the information source that we talked about earlier. So for instance, my voice, if I were to capture that electronically in an analog fashion, has a bandwidth of, let's say, 5 kilohertz. If you have a really high voice, maybe it's 7 kilohertz. If you're trying to transmit music with really high fidelity, maybe it's 20 kilohertz. Now, how big would the antenna be if I wanted to transmit data directly at 20 kilohertz? Anybody have a guess? Use the microphone.
100-something thousand kilometers.
Okay. You can do math faster than I can, but basically it's simple. Lambda f is equal to c, where c is the speed of light. And so your antenna needs to be on the order of the size of the wavelength. So if you go to really low frequencies, the wavelength is huge. It's hundreds of thousands of kilometers at kilohertz. You can verify that. And so you have to build an antenna that's basically bigger than the Earth. Not a very practical situation. So generally, we like to use higher frequencies where we can make our antennas smaller. In fact, if you think about gigahertz frequencies, where the wavelength's on the order of centimeter, you can see that that's at 10 centimeters. That's actually kind of optimal, right? Because at 10 centimeters, that's really nice and small, and something that you can put inside of a laptop or in your cell phone. And that's why those frequencies are so popular for mobile communication. Now, that means that our information has to be carried by another signal that's at higher frequency. And the way we get our information onto that carrier is to use modulation. And there's many different ways of modulating. We'll talk about that in this course. Very generically, if you guys have taken 120, you already know several different modulation schemes. We have AM, where basically we change the amplitude of the signal that we're transmitting. That's amplitude modulation. If you've ever used an AM radio, you've had experience with amplitude modulation. Of course, I can also change the phase of my signal. That's phase modulation. Or if I change the frequency of my transmitted signal, it's frequency modulation. And of course, we're all familiar with all these different ways of doing modulation. Now, most of the modern communication systems we build actually are digital. So we don't change the amplitude in a continuous fashion. We change it, let's say, in a discrete fashion. So there's a whole host of digital communication techniques which use some combination of either amplitude modulation or phase modulation or some combination of that. And we'll talk a lot about that in this course. So how do we choose the carrier frequency? Well, we already talked about the fact that using higher frequencies means we can make smaller antennas. Of course, if you go too high in frequency, your circuits won't work. So there's kind of an optimum frequency, if you like. But life isn't so simple. It's not just determined by technology. It's also a legal thing. The FCC in the United States tells you what spectrum you can use to transmit. And spectrum is a very important resource. It's a shared resource. You can't just arbitrarily pick a frequency and start transmitting. If you do that, you'll find out how quickly you can get arrested, especially if it's an important frequency band like emergency bands. So there's basically spectrum allocation that tells you, yes, this spectrum is allocated for, let's say, industrial, scientific, medical uses. There's bands where you're free to transmit as long as your power level is lower than a certain threshold. That's a good example of the wireless LAN band. You guys can transmit as much as you want in the wireless LAN band. No one's going to come and arrest you because that's an ISM band and you're allowed to transmit. But your power has to be lower than a certain threshold. If it's above that, technically you can get arrested, or you'll annoy a lot of people who may beat you up. Either way. I heard that the Eiffel Tower was initially built as a radio transmitter, but I went and looked that up on the Eiffel Tower website, and actually that's not true. I think it was built for aesthetic reasons first, but then people realized, hey, this is a great way to send signals as well because it's so tall. So back in those days, technology didn't allow you to operate at high frequencies. So to build a radio, you had to use low frequencies, hundreds of kilohertz, tens of kilohertz, and so the antennas were huge. Now the other constraint about that we already touched upon a little bit is bandwidth. So there's, depending on what kind of information you're transmitting, you have to also take into account how much bandwidth you're going to occupy. So in other words, if I'm going to transmit voice at 1 gigahertz, I may only need about 10 kilohertz of bandwidth. Maybe 100 kilohertz if I want to transmit FM. That's a very small fraction of the bandwidth. So I could, let's say, allocate frequency from 1 gigahertz to 1.01 gigahertz and have a bunch of channels in there. But if now I want to transmit, let's say, data, high-speed data, let's say wireless LAN, then I may need 10 megahertz of bandwidth or 50 megahertz of bandwidth. And so then the number of channels that I can use goes down. So generally, the higher the data rate, the higher the frequency, because you can have more channels. And I put down some numbers here. High fidelity audio is about 20 kilohertz of raw bandwidth. Now, if you modulate that linearly onto a carrier, the bandwidth doesn't change. So if I just AM modulate, bandwidth's about the same. If I do some kind of nonlinear modulation like FM, there's actually a big bandwidth expansion. I need about 10 times more bandwidth. To send video, you need about basically a megahertz to 10 megahertz, depending on what kind of quality we're talking about and how big that little screen is on your computer. For instance, wireless LAN uses about 22 megahertz. So in theory, you could send video signals through that. So if you look at the carrier frequencies that are allocated today, very common frequencies, most of you, I don't know your generation if you guys still use radios, but if you do, 100 megahertz, right, is FM radio. If you watch TV, I don't know if you guys watch TV anymore, right? You guys have the internet. Why would you watch TV? If you watch TV, it's around 600 megahertz. UHF, as an example, it's actually from much lower frequencies. VHF is at low frequencies. UHF is the high band. If you go a little bit higher in frequency, let's say 900 megahertz, that's where all the cellular bands start, and also the cordless phone. So you have a cordless phone, there's a very good chance that it works either at 900 megahertz or at 2.4 gigahertz. There's also a bunch of cellular bands starting around 800 megahertz and ending around 2 gigahertz. And they have all sorts of names, PCS, cellular, this and that. It's all the same. Of course, ubiquitous wireless LAN nowadays. We all know and love our wireless LAN systems. They operate at 2.4 gigahertz and 5.5 gigahertz. And these days, actually, there's a whole flurry of activity in using spectrum in different ways for basically mostly for data applications. For instance, 3 to 10 gigahertz has been proposed as the ultra-wideband. Ultra-wideband because it's so much bandwidth. It's 7 gigahertz of bandwidth. Don't get too excited, though, because the amount of power you can transmit in that bandwidth is only about a milliwatt. But people envision this as a very short-range, high-speed link. Let's say like your USB cable without the cable, or wireless USB. So there's lots of spectrum out there, and it's being used in new ways. Another way that spectrum usage is changing is in the past, spectrum was allocated in a very fixed manner. You know, the FCC said, you can use these frequencies, you're allowed to use these frequencies, you know, at these times, or you can buy this spectrum and use it privately and no one else can use it. Nowadays, we're exploring ideas of sharing spectrum, and a lot of it comes about because of wireless LAN. People saw how great wireless LAN is and how well it works. Why not do that with other spectrum? An example of a spectrum that people would really like to go after is this UHF spectrum. And the reason is that UHF is probably one of the sweet spots in the spectrum in the sense that you can get very good long-range transmission with reasonable antenna sizes. It's very good at bending corners and going through trees and walls and whatnot. And frequency is still low enough that you can build very low power circuits. So it's almost like an optimal frequency for building, let's say, wireless internet. But today that spectrum is owned by the broadcasters, the television broadcasters. So there's a lot of talk of building so-called cognitive radios, or radios that basically could figure out that no one's watching television on a particular station and use that spectrum for, let's say, wireless internet. So there's a lot of new ideas that are coming out for spectrum usage. Okay, what are some of the other big ideas in building a wireless system? Well, another big building block in a receiver and a transmitter is what we call a frequency synthesizer. And as the name suggests, we synthesize a very precise frequency. Now, most of you have used a frequency synthesizer. If you've been in the lab and you've done an experiment, and the experiment was set the input to 10 kilohertz with an amplitude of 1 volt, well, inside that little machine there's a frequency synthesizer that generated that tone for you. In a wireless communication system, we often use a frequency synthesizer to generate that LO, that local oscillator, which is used in the mixer, let's say for frequency translation. As we'll see later on in this course, we can also build very nice phase modulators and frequency modulators by using something which is called a phase lock loop. And again, we're not going to go into the details in this lecture, but think of a phase lock loop as a system that takes this oscillator and it locks it to this frequency, some multiple of this frequency. So for instance, this might be a gigahertz signal and this might be a 10 megahertz signal. And this loop is a feedback loop. It's a negative feedback loop that locks the frequency, the high frequency signal, to the low frequency signal. Now, why would you want to do that?
Synchronization with clocks.
Okay, you want to use the mic?
Synchronization of the clock
Okay.
from the system and the broadcaster.
How does using 10 megahertz, let's say, help you? No, you're right. But the key point is that in order to communicate, we need to agree on our clocks, right? We need to have the sender and receiver need to have clocks that are well synchronized. And you're exactly right. One way to do that, a clock and data recovery system will take the clock of a received signal and it'll regenerate a new clock, which is based on the data. That's more at the baseband. For let's say the FCC says you can use 1 gigahertz to transmit data. Well, what's 1 gigahertz, right? If you build an oscillator that oscillates at 1 gigahertz and you change the temperature, you'll find that all of a sudden it's 1.01 gigahertz. Is that bad? Yeah, it's bad, right? Because we're allowed to transmit at 1 gigahertz. Turns out if you build an oscillator, which we'll do in this class, it's not very stable. Its frequency is not stable. It varies over temperature. It varies over process. As we'll find out, it actually just varies on its own. Just the noise in the system naturally gets multiplied and makes the oscillation frequency vary. So phase lock loop, what it does is it locks that oscillator onto another signal, which is presumably much more precise. And in fact, anybody know what we call that precise signal? Exactly, it's a crystal. So a crystal is it's a mechanical resonator which resonates at a very precise frequency, and we can use that as a reference to generate a high frequency signal. Okay? Any questions up to here? Now keep in mind this is an introduction. You should come back to these slides later in the course and reread them because I think it'll make a lot more sense to you at that point. Okay, so we looked at the receiver. We also looked at a frequency synthesizer very briefly. Let me just say a couple more words about the frequency synthesizer. In this course, we're going to spend a lot of time building oscillators. We're going to learn how to build oscillators inside and out. Most of the oscillators we build will be LC oscillators, if you're familiar with that term. We also will touch upon how you build a frequency synthesizer. In particular, we'll look at how you build a frequency divider, how you build a phase detector or a phase frequency detector, and basically this is a low-pass filter. I assume you know how to build a low-pass filter. But we'll talk about how you stabilize this feedback system. It's actually a acute feedback system because it involves a lot of nonlinear components. And we'll find that we can linearize this system over a small range and analyze it as if it were a linear circuit. So we'll talk about that also later. Okay, transmitter is a dual of a receiver, but it's very different. The kinds of constraints that you have when you build a transmitter are very different. In particular, a transmitter, again, a generic transmitter starts out with some digital bits, converts them into analog signals, multiplies it by a local oscillator, which is generated by the synthesizer that we just discussed. There's that little crystal symbol that somebody brought up. This is our precise reference frequency. So now we've translated our, let's say, baseband signal, the bits, into a precise RF signal, very precise frequency. And we can also set the amplitude very precisely with, let's say, a VGA, a variable gain amplifier. And finally, we run that into a power amplifier. A power amplifier is designed to put out a lot of power into the load. The load might be the antenna, it might be the cable that it's driving, but usually we'll find the load is a relatively small impedance, something like 50 ohms, 75 ohms, or 300 ohms. If you're basically looking back to your analog course, most of the loads that you're used to driving are capacitive loads, right? or high impedance loads. In this class, often we'll be driving low impedance loads. Okay, so we'll spend a lot of time on the power amplifier because it turns out that the power amplifier is the most power-hungry block in your radio system, in your any kind of generic communication system, because it turns out that it's very hard also to build an efficient power amplifier. So if you build a power amplifier based on what you learned in 140, I can guarantee you the efficiency won't be better than a couple percent. It's actually quite shocking. You know, a lot of times you go out there in industry and you find people building things that are power drivers and they're using linear circuit techniques, and you find the efficiency is actually pretty dismal, a couple percent at best. In this class, we're going to learn to build power amplifiers that have theoretical efficiencies that approach 100%. Practical efficiency is always a different matter, but at least 50% we'll see. And that's very important because, you know, in today's world, it's all about mobility and it's all about energy saving. So if we're, you know, efficiency is how much power how much DC power we take and convert into RF energy. So if our efficiency is 1%, that means that 99% of the energy is just being wasted. And wasted means it's heating up this room, right? Okay, so the transmitter spectrum, of course, is different from the receiver spectrum because we're transmitting a strong signal. I call that the fundamental here. There's also a noise floor associated with the transmitter. Usually the noise floor is not too hard. Because we're sending such large signals, we just have to make sure the noise floor isn't too large so that it interferes with other users, but that's not too hard to do. What is an issue is distortion that's generated by our power amplifier. And distortion is basically, you know, as we all know, a linear system takes an input power and basically turns it into output power with some gain. A nonlinear system, unfortunately, can generate new tones. Basically, it can translate the input frequency to different output frequencies. So here, our power amplifier, even though it's designed to be linear, it generates what we call, let's say, harmonic distortion. So harmonic distortion is energy at the second harmonic. So if this is frequency 1 gigahertz, we find there's a tone at 2 gigahertz. We also find there's a tone at 3 gigahertz. That's the third harmonic, and so on and so forth. And why are these tones bad? Who cares? Let's just transmit them. Why do we not want to transmit these tones? Okay, I'll use the mic.
They may be in somebody else's channel and now we're causing interference?
Exactly. You know, if we want to use the spectrum, if we want to be good users of the spectrum, on the receive side, we have to be good users on the transmit side as well. So we basically want to transmit information in the bandwidth that we've been allocated, and we want to transmit as little junk outside of that bandwidth as possible. In fact, there's usually a spectral mask that we have to satisfy, which is again set by the standard of communication that we're using. So, of course, I can use filtering to get rid of these harmonics, right? That's not too bad, you know, big deal. Build a little filter, a low-pass filter, you get rid of that. Well, as we'll learn in this class, distortion is not only generated at harmonic frequencies, but intermodulation, cross-modulation distortion is also created at our own frequency. So if the PA is very nonlinear, it will generate distortion in band, which will actually corrupt the signal that you're transmitting. And we'll learn how that happens later on in the course. Also, there's what we call spurs. Spurs usually occur in the frequency synthesizer. You know, the frequency synthesizer, again, is supposed to synthesize this pure tone, but as we'll learn in this class, it doesn't do that. It also synthesizes lots of spurs, different frequencies which are related to the different clocks that we're using in our system, let's say the reference clock. And these spurs, usually it's either the spurs or the harmonic distortion that determines the spurious-free dynamic range of our signal. That's the difference in dB between the power that we're transmitting and the power of the largest spur. Okay? Again, the spurs may occur in band where they're hard to filter. Okay, so I'm not going to read this list in detail because I don't want to bore you guys. But this is kind of a course outline, what topics we're going to cover. We're going to start out on familiar territory, high-speed amplifiers. So basically, it's 140 kind of material, but we're going to go into it a lot deeper. In particular, we're going to be really concerned with bandwidth. We're going to try to design amplifiers that have as much bandwidth as possible. We're also going to be very concerned about operating at higher frequencies. We're going to try to figure out how do we build amplifiers that work at the highest possible frequencies. What are the limitations, basically? Why can't I take a transistor and operate at 100 gigahertz? What's the limitation? If I had to change the process, what would I change in order to allow me to operate at these higher frequencies? In doing that, we're going to look at basically tuned amplifiers. We're going to look at impedance matching to try to build optimal amplifiers. We're going to look at matching networks, pi matching networks, L matching networks, T matching networks. We're going to look at transformers, both magnetic coupling transformers, capacitive transformers, so on and so forth. And we're going to look at different technologies. Our focus is going to be primarily CMOS and bipolar technology. Every once in a while I may make a comment about a MESFET device or a JFET device, but don't worry. The main devices that you need to know in this class are CMOS devices and bipolar devices. Now, last year when I taught this course, someone raised their hand and said, "Why are you teaching bipolar? That's useless. Nobody uses bipolar anymore." Well, unfortunately for you guys, that's not the case. Bipolar devices are very important, and they're pretty widely used in industry, especially silicon germanium bipolar devices. Now, silicon germanium bipolar is a lot like standard bipolar that you guys know and hopefully love, but silicon bipolar transistors, silicon germanium, are actually HBTs. They're heterojunction bipolar transistors, which means that they actually, from your perspective, the small signal model looks the same. Only difference is that RB is smaller and FT is higher, so it's nicer. Now, also when we discuss amplifiers, we're going to spend a lot of time discussing noise, because this is one of the limitations. You can't just arbitrarily design amplifiers and get lots of gain. We also have to pay attention to noise. And I think noise is a new topic for a lot of people, so we'll spend some time talking about where noise comes from, how do you analyze circuits that generate noise, and then finally, how does noise impact the communication system, and how do you basically design good amplifiers that generate as little noise as possible. And then moving forward with amplifiers, we're going to talk about distortion. This is going to be a big topic of this course, a few weeks at least, and we're going to look at the sources of distortion. We're going to look at amplifiers as large signal circuits. We're used to linearizing amplifiers and looking at them as small signal circuits where it's purely a linear device. What we'll find in this course is that there's actually quite a bit of nonlinear behavior, which is very important in communication systems, and we're going to analyze the distortion generated by these devices. We'll also look at how to reduce distortion, and feedback turns out to be a great way to reduce distortion, so we'll spend some time on that as well. Okay, so in some ways, amplifiers is something that you guys know. We're extending your knowledge, talking about distortion, noise, wideband operation. The next few topics hopefully are going to be really interesting to you guys because they're going to be new. We're going to talk about mixers and oscillators. As we discussed, mixers are circuits that perform frequency translation. They're either nonlinear circuits or time-varying circuits, so we're going to have to learn to analyze them. Turns out that SPICE, actually standard SPICE, is not a very good tool for analyzing mixers. It's very slow. There are better tools for analyzing mixers, namely harmonic balance simulators and periodic steady-state simulators, such as Cadence Spectra RF, and that's when we're going to learn about these simulation tools. We're also going to look at oscillators, as we've already discussed. Oscillators are, again, very nonlinear blocks. They take DC power and they generate a tone at RF frequency. We're going to look at how you design oscillators, how you analyze them. We're going to look at their amplitude stability, their frequency stability. We're going to look at the waveform properties, such as the waveform distortion, and lots of different oscillator topologies. Another big topic in this course will be power amplifiers. I touched upon this already. We're going to look at different classes of power amplifiers and how much power gain we can get out of our devices, how much efficiency, how efficient they are, how linear they are, and how much stress they put on the devices themselves. Power amplifiers operate with large voltages, and so there's actually quite large voltages and large currents because it's power, right? Power is voltage times current. So obviously we're going to put a lot of stress on the device, not just large voltages and currents, but also high temperatures. And that's kind of an overview of a list of topics. Any questions or comments up to here? Okay. So we can actually go to lecture 2. And this is a good time to give you guys a warning. So last year when I taught this course, it was on the blackboard, right? So there was a natural speed reduction, right? I had to write things. So this semester I'm teaching from slides. I can go really fast. So unless you guys want to learn a lot more than, if you want me to go really fast, I'm happy to do it. But at some point it's a good idea to slow me down. So I'll do my best to pace myself, but if you find that something is unfamiliar to you, basically ask questions. You don't feel stupid for asking questions. I actually really enjoy the interaction. The course notes are online. There's a couple of good reference books for the textbook. I guess I should mention that as well. I should talk about that. And so you might say, why am I even coming to this class, right? Even the lectures are webcasts. Well, the reason you're coming is hopefully to also interact a little bit with me and ask questions and interact with your peers. So I encourage you guys to do that. That brings up the textbook, which I forgot to mention. There actually is no textbook for this course. All the lecture notes will be online. I have a couple of textbooks listed as reference. The first book is Professor Gray and Professor Meyer's book on analog integrated circuits, design analysis of integrated circuits. Highly recommended. It's a great reference book to have on your shelf if you want to impress your friends. But no, more seriously, it's got a lot of good material. If you want to review feedback, this is a good time to go and check out that book and read the chapter on feedback, because we're going to be using a lot of feedback circuits in this class. There's also a couple of books that are more specifically on communication circuits and RF integrated circuits. One is Professor Tom Lee's book from Stanford called RFICs, CMOS RFICs, and as the title suggests, it's mostly about CMOS, but actually it's about building communication circuits in general as well. So the title is a little bit misleading. In particular, I really encourage you guys to read chapter 1 of that book this week. It has a history. He calls it the nonlinear history of radios. Very good reading, really interesting stuff. That book is on reserve for you at the library, but also feel free to get a copy for yourself. Another book is Professor Razavi's book from UCLA. I think it's called RFICs or something like that. Anyhow, RF microelectronics, yeah, something like that. It's also a good reference book, especially on system issues. A lot of times in this class, we're going to be kind of worm's eye view. In other words, we're going to be digging deep in the ground to understand communication systems, and it's useful to have a bird's eye view. So if you want a bird's eye view and think about the overall system, what are we trying to do, what are we trying to accomplish, that book is very useful, especially if you're having some trouble understanding some general communication system concepts, modulation, demodulation, noise, and so on and so forth. Different ways of sharing spectrum. There's some really good readable, easy to read chapters in that book. I'll do my best to also give you guys pointers to what sections in the book overlap with our material, so that if you are really into reading outside references, you'll have a place to look. But they're totally optional. If you come to class, if you read these lecture notes and you understand them, you'll do great in this class. You don't have to do any outside reading. Okay? Any questions about the book? The books? Good. Can you use the mic? Sorry, I'm going to remind you guys until you get into the habit.
Yeah. At the end of each lecture, like put sort of like suggested readings or references.
I'll try to do that. I'll try to put it on the web page. Yeah.
Thanks.
Okay. Any other questions or comments? Okay, so let's start lecture 2. So lecture 2 is hopefully a review for most of you. We're going to look at MOS and bipolar technology. And more specifically, we're going to look at high-speed applications. Okay, so basic review, right? This is all piece of cake kind of material. If we look at single-stage amplifiers, if we're going to use a transistor, it's a 3-terminal device, right? And we're going to take one terminal in common to create a 2-port. That means we have choose two different topologies. And we can take the source node in common, or the emitter node. That's a common emitter amplifier. We can take the collector node in common. That's a common collector amplifier or common drain amplifier. Of course, we know that more commonly as an emitter follower or source follower. Or we can take the base or the gate in common, and we have ourselves a common gate or common base amplifier. Now, all these amplifiers are good and well, but usually we don't use them. And that's because each one has a weakness. Now, let's start out with the common source amplifier. The common source amplifier, common emitter amplifier, the strength that we should mention is gain. It has lots of power gain. In this course, you're going to get into the habit of thinking about power gain. I know up to now you've thought more about voltage gain or current gain. In this class, power is money. Okay, so power gain means you have to have current gain and voltage gain, right? So common source amplifier is good because it has both. What's bad about a common source amplifier? Well, we all know that the weakness of a common source amplifier is bandwidth reduction due to Miller effect. Miller effect happens because we have a parasitic capacitor from the base to the collector. And it's a pretty small capacitor. It's something you might be able to live with. But if you're greedy and you try to get lots of voltage gain out of this device, we know that we get Miller multiplication. In other words, we get a capacitance at the input which is Miller multiplied by the voltage gain. So if the voltage gain is 10, this small capacitor is all of a sudden 10 times bigger, and it appears at the input. And that means that it's going to basically produce a low-pass filter at the input of the amplifier. And depending on the source resistance, if you're voltage driving this amplifier, that might not be a problem, but usually you're driving it with some source impedance. Source impedance might be your cable characteristic impedance. That's going to produce bandwidth reduction. So that's the problem with a common source amplifier, and we can solve that problem by operating with low source impedances. And in fact, in a lot of communication systems, that's pretty easy to do because, as I mentioned earlier, we have low impedances. Cable impedance might be 50 ohms or 75 ohms. What are some other problems with a common source amplifier? Anyone? It's all review material, right? Why not just go out and build all our amplifiers with a common source amplifier? Use low source impedances so we have lots of bandwidth. Yes, Mike.
I don't quite remember exactly, but it has to do with output impedance.
Okay, that's a good point. Let's not worry about that now. We could always buffer. We could put a buffer in there and get any output impedance we want. What are some other properties of, okay, in the middle?
Is there a problem with swing? Voltage swing?
Okay, actually the swing is pretty good on this amplifier, right? It can swing all the way to supply, and it can swing all the way down to either VD-SAT or VCE-SAT. So that's pretty decent swing. Okay, certainly it has almost no power supply rejection, right? Any signal you put on the power supply leaks right into the output. So that's a potential problem. But, yeah, so that's one problem. There's some other things. Let's see.
Referring to lecture 1, the gain is fixed.
The gain is fixed. Okay, that's actually, when you design a variable gain amplifier, you might use a specific topology that lets you vary the gain. Let's not worry about that for now. Let's say we're designing a fixed gain amplifier.
I don't know, you might have talked about this, but in order to increase your gain, you have to have a large resistor, and so that takes up a lot of area.
Okay, that's a good point. It's not necessarily the area, it's the capacitance of a large resistor and the bandwidth reduction, right? So even if we don't have a limitation coming from the source, from the load we have output capacitance, and that produces a pole with that load resistance. So that's bandwidth reduction. And you're precisely right. If I want to get high gain, I need to use either a lot of current to get lots of transconductance, or I need to use a large resistor. And if I use a large resistor, that's going to reduce the amount of swing I have at the output, and it's also going to have a lot of capacitance and a low RC time constant, or high RC time constant. But I'm actually looking for something else. Let's not get into that now. We'll talk about distortion a lot, but you're getting hot. That's a problem. Noise, okay. Yeah, let's not worry about that. I don't expect you guys to know that. It's something you guys know from 140.
Are there stability issues?
Stability, okay. single-ended and not differential. Yeah, these are all problems, but looking for something else.
Is it not linear?
Not linear. That's something we'll talk about later, linearity. Zero in the right half plane. Again, you're getting too complicated. Something simpler. There is feed-through from the input to the output, which does produce a zero in the transfer function. But it's actually not temperature stable, right? And it varies a lot with process, right? So if I have this, the gain of this device is GM times R. GM varies over temperature, it varies over process. R varies over temperature, varies over process. It's not a very robust amplifier, right? If someone says, give me an amplifier that has a power gain of 10, and you give them this, it's going to vary all over the map. So how do we fix that? Feedback, right? That's right. Okay, good. Okay, so how about a source follower? What's the problem with the source follower? Well, the source follower is a nice amplifier. One of the issues is that it has a very high input impedance, and actually it's an issue also with the common source amplifier, which we didn't really talk about. We'll learn about that later. It's hard to match the input if you're trying to get a matched input impedance. But as you can see, a source follower also doesn't have voltage gain, right? In fact, it has voltage gain roughly equal to 1, but it has lots of current gain. So its power gain is certainly going to be less than a common source amplifier. What about the bandwidth of a common source amplifier? Well, the bandwidth is very good. It's a very wideband stage, and that's because there's no Miller multiplication. You can see the voltage gain from here to here is 0 because I've grounded this node, so the Miller capacitor just appears in parallel with the input. The device capacitance, let's say C pi, is in a sense bootstrapped. That's because the voltage across the nodes are almost equal, so very little current flows into that capacitance, and therefore it's very wide band. Another way to look at this is the input impedance is highly degenerated, and so that feedback, the degeneration produced by RL, is basically going to reduce the input capacitance. How about the common base amplifier shown here? Again, common base amplifier, it's wideband. It doesn't have the same issue with the Miller effect, but it doesn't have any current gain. It only has voltage gain, so it's not going to give us as much power gain as a single stage amplifier. Now, I'm not saying that they're bad amplifiers. They're very useful. They're particularly useful when we use them in conjunction with other amplifiers. In other words, when we have 2 stages or 3 stages, or if we use feedback. As we'll also learn later in this course, the common source amplifier is actually probably the best amplifier, not only in terms of power gain, but also in terms of noise performance. So if we're trying to design an amplifier that has a very low noise figure, this is the topology of choice. So all we need to do is somehow fix this and make it more robust. Now, one way to fix these amplifiers is simply to go to 2 stages. And 2-stage amplifiers are very convenient, especially for integrated circuits, because transistors are really free. They're tiny. They take up very little area. So if you had to choose between a single-stage amplifier and a 2-stage amplifier, an area were a concern, it basically would not be a concern because transistors are so small in modern technologies. So we try to use transistors, more transistors, to improve the performance of, let's say, amplifiers. Now here I have the first popular wideband 2-stage amplifier. It's basically a source follower followed by a common gate amplifier. And you can see that now the power gain of this cascade is actually pretty good. It's a 2-stage amplifier. The first stage only has current gain, the second stage only has voltage gain, but in cascade it provides nice voltage gain and current gain, so I get a good power gain out of it. It also lets me have a high input impedance, which is not the case with a common gate amplifier. Common gate amplifier has low input impedance, so that's nice. Does this also look familiar to anybody? Is there a popular amplifier topology that essentially degenerates to this? What's that? Diff pair, exactly, a differential pair. Think about this as the common source node, right, going to ground. I've grounded one input, and I'm driving a differential pair single-endedly. And that's a very nice wideband amplifier topology. You can see it doesn't have Miller effect because the first stage, by definition, doesn't have Miller effect. It has no gain. And the second stage, there's no feedback capacitance because, or there's very little feedback capacitance. Usually it's mostly due to layout. but there's no intrinsic feedback capacitance in the small signal model. Okay. Any questions or comments about that? All right. Another way to build a useful two-stage amplifier is basically one of the big problems with our common source amplifier was the Miller effect, right? And we mentioned that if you have a low source impedance, Miller effect's maybe not too bad. Well, one way to generate a low source impedance is just to buffer the actual source impedance. So if I drive this amplifier with high source impedance and I use this source follower, the source impedance now is roughly 1 over GM, the source follower impedance, output impedance, which can be very small if I can push enough current through that device. So I fix the source impedance to a low enough value so that, let's say, the Miller capacitance doesn't degrade the bandwidth too much. So this is one way to do it. But there's actually a better way to do it, and that's the amplifier that we all love, the cascode amplifier, right? The cascode amplifier takes common source amplifier